So on this video, I just want to go over some quantum gates. So before, a few lectures ago, we brought up classical gates. We brought up something called the NOT gate, NOT, which said if this was a 0, that was a 1. If this was a 1, that was a 0. We also brought up something called the AND the OR gates. There was our AND, A and B, and this was our output. And this was 0 unless both A and B were 1. But these are all physical wires coming out made up of transistors and so on. Right here. These are classical gates, computer gates. I wanted to bring up quantum computer gates. Quantum computer gates are usually a lot different. They might be a polarizer, it could be a magnetic field, so it's quite a bit different right here. But we can still go through the gates. One of the gates here, sometimes you call it an X gate, or we could even call it a NOT gate. It's kind of a NOT gate right here. And so I'll just draw it like all my gates like this right here. Here's my X gate. It's got one input and one output right here. And if this is a up, this will become a down. If this was a down, it would flip it up to the up right here. So each time you do this, this is really a matrix that we're looking at, this X. And for the X gate, this matrix is 0, 1, 1, 0. Why? Because if I operate X on up, so this is 0, 1, 1, 0. If I operate on up, which is 1, 0, what do we get? We get 0, 0. Here we get 1, 0, 1. You notice we operate X on up, we got the down. Likewise, if I operate on the down, I should get the up. 0, 1. We get 0, which gives us a 1 at the top, and then 0, 0 on the bottom. So that's the up. So my X operating on up, down gave me an up. X operating on up gave me a down. So there's my X. You notice if I run it through twice, right here, I come back to the same thing. That is, if I take my X gate and I operate, say, on up, and I operate it on a second time, well, that better give me back to my up again. Because it went from up, down, back to up again. Which means that this XX multiplied by itself should just be the identity matrix, I. So if I multiply this by itself, it should just give, let's just see if that is true, 0, 1, 1, 0 times 0, 1, 1, 0. Well, that gives me, for this item right here, it's 0 plus 1, which is 1, 0, 0, 0, 0, 1, 0. Which means I got the identity matrix, which means that these are inverses of each other right here. So that means that is equal to itself. So running it backwards and forwards, this would be called a reversible gate. Running it through a second time reverses what the first time did. All single input computer gates are going to probably be reversible like this right here. And what is this actually doing? Remember we had a block sphere. You know, it was this ups and ins and right. This right was really the x-axis, and this was really the z-axis, and this was really the y-axis. But applying an X gate on this thing really just rotates about the x-axis by pi. So it went from here down to here. So So every gate, computer gate, just takes this sphere and takes a vector and just moves it around. That's all you're doing to every computer gate there is, all the quantum gates. Okay, I should say, which is kind of strange, is there's also something called the square root of a NOT gate. Square root of a NOT. Square root of the NOT gate. Well, what would the matrix of that be? It'd be the square root of this. It'd be 0, 1, 1, 0 to the 1/2 power. Okay, so, well, if a knot goes from an up to a down, what does the square root of a knot go from? Up to, that's kind of strange right there. Well, you can take the square root of a matrix right here. I'm just going to give you the result of it right here. This is just 1/2 plus I over 2, 1/2 minus I over 2, 1/2 minus I over 2, and 1/2 plus I over 2. I guarantee if I multiply this by itself, I should get 0, 1, 1, 0. Okay, you can check that out right there. So that means if I just operated this square root of the knot on, say, the square root of the knot, let's say on an up state, which is 1, 0, right here, what would that give me right here? Well, if I put this in for that right here, I guess we'll write it down. 1/2 plus I over 2, 1/2 minus I over 2, 1/2 minus I over 2, 1/2 plus I over 2. If I operate that on 1, 0, what does that give me? Well, it gives me this plus 0, so it just gives me 1/2 plus I over 2. And on the bottom, it gives me this plus 0, 1/2 minus I over 2. So this right here, it'd be 1/2 plus I over 2 up plus 1/2 minus I over 2 down. That's what the square root of up would be. Now I imagine if I took and did another square root of another square root of knot on this, that is, if I took the square root of the knot of another square root of knot, acting on up, that means I'm taking the square root of just on this. I imagine this will give me what? Down. Why? Because the square is just a square root of, that's just a NOT gate on up, gives me a down. So if I took this and put this guy in up here, it would just give me the down state. So it's kind of strange to have a square root of a knot. You wouldn't get that. There's nothing like that in classical mechanics. Okay, that's just kind of a little sidebar right there. We also have, the reason why they call this the X gate is because it's very similar to my S sub X. Remember my S sub X right there? Matter of fact, I have it right here. It looks just like that, except here we have the H bar over 2. Take away the H bar over 2, and that's my X gate right here. We also have something called the Z gate. The Z gate right here. And that has, if the matrix would be 1, 0, 0, minus 1. If you look over here, the reason why it's called the Z gate, it looks just like this without the H bar over 2. I imagine there'd be a Y gate too, but I'm not going to bring up that one. I don't need that. Okay, so what does the Z gate do? So if you have a Z here, Here's your input and here's your output. If you put in an up, what you get out is the up. It doesn't do anything to ups. If you put in a down, what that gives you is minus down. Now, is it minus down up? No. Minus down is minus down. It's not up right here. Okay, so if we were to take this and operate on 1, 0, we should still get 1, 0. If we take this and operate it on 0, 1, we should get minus 0, 1. Okay, I'm not going to... But there's the Z gate right there. Again, if you run it through twice, you should get the same thing back again. So that is the Z times the Z, again, should be the identity matrix, or these should be equal to its own inverse. So this is equal to the identity matrix. You might say, what the heck does that do? Well, if you remember what right is, wasn't right 1 over the square root of 2 up plus 1 over the square root of 2 down, and left was 1 over the square root of 2 up minus 1 over the square root of 2 down. So you'll notice if I were to plug in a right into here instead, well, it doesn't do anything to the ups, but it turns the down into a minus down. Well, that would turn it into a left. So if I put in a right here, it would turn it into a left. If I put a left over here, that would turn it into a right. So, so that turns it into lefts and rights. Okay. That's the Z gate right here. Now, there's a gate here. We won't be using it, but it's probably the most dominant computer gate there is. It's called the Hadamard, Hadamard, Hadamard gate, which is called the H gate. And that is 1 over the square root of 2, 1, 1, 1 minus 1. That's used more than any other gate in for all the computer gates right here. What does that do on an upstate? That is, what is H on the upstate? Well, we put that in. That's 1 over the square root of 2, 1, 1, 1 minus 1 on the upstate, 1, 0. Well, what does that give me? That gives me 1 over the square root of 2. And then we get 1 plus 0, that's 1. 1 plus 0, that's 1. So this is 1 over the square root of 2 up plus 1 over the square root of 2 down, which is my right. So operating H on up gives me the right. Operating H on left, which is down, gives me the left. If I run it through a second time, if I operate on right, I'll get the up. If I operate on left, I'll get the down. So it switches it switches up and rights, back and forth, and down and lefts. That's all it does. And since you get the same thing when you run it through twice, H times H should be the identity matrix, or their inverses. Everything's reversible right here. So it's just used a lot right there. So that means if I have, say I have the upstate, and I apply an X to it. If I apply an X to it, it turns it into a downstate. So over here, if I apply an X to it, it turns it into a down, or if I had a down, went this way, it would turn it into an up. Now, if we have our up state and we apply it to H right here, then it turns me into a right state. Or if I had a down and I applied the H gate, it would turn me into a left. This would turn me into a left gate right there. And this Z gate turned rights into lefts and lefts into rights. So this is the Z gate right here. So if I wanted to go from here, let's say from an up to a down, I have to apply what? An X gate to it. Or if I went this way, I'd have to apply an H gate, then a Z gate, then another H gate. So H gate, Z gate, and H gate is the same thing as an X gate right there. And we could have done that. We could have multiplied out these three just to see if we do get the X gate. The H gate was right here, 1 over the square root of 2. I'm going to get another 1 over the square root of 2 on the other H gate, so I'll just pull out the 1/2. And we would have the H, which is the 1, 1, 1, minus 1. Then we had the Z, which is right here, 1, 0, 0, minus 1. 1, 0, 0, minus 1. And then we had the H again. 1, 1, 1, minus 1. Okay, so I guess I'll multiply these two first right there. So we have the 1/2, 1, 1, 1, minus 1. Then over here, we get 1 plus 0, that's 1. The other one, we get 1 plus 0, that's 1. Over here, we get 0 minus 1. And the last one, we get 0 minus 1 times minus 1 is plus 1. Okay, and then multiply these two together. 1/2. So the first term I get is 1 minus 1, that's 0. The other term I get is 1 plus 1, that's 2. The other one is 1 plus 1, that's 2. And the last one is 1 minus 1, that's 0. Throw the halves in there, and that's just 0, 1, 1, 0. And that should be what my X gate was. Yeah, 0, 1, 1, 0. So you get the same thing right there. Okay, one other gate I want to go through, and that is something called the C0, the SNOT gate, C0. It actually stands for controlled not. It looks like this. It's a 2-bit system. It takes 2 bits right here, and it looks like that right there. This one they call the control, and this they call the target. Okay. Now, the control never changes. So if this is an up, it's going to stay up all the time right here. It never changes. But what the control is going to do, he's going to control what happens on the target right here. Now, if the control is up, then these two are going to stay the same. Don't do anything. So if control is up, leave the target alone. Leave target alone. Okay. But if the control is down, then flip the target. That is, if this is then up, then the target flips. What does that mean? It means up goes to down. So if this was an up, this would go to a down. If this was a down, it would go to an up. That's all that does right there. Now, remember, this is this, if I wanted the matrix for this, it would be a 4 by 4 because this is 2 bits right here. And so the C naught, it's really C naught. This thing would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. That's what it would be. Now, you remember when we had 2 bits right here, my psi, we had alpha 1, beta 1s, and alpha 2s, but I'm just going to use one constant. We had something like an alpha 1, 1, up, up, plus alpha 2, alpha 1, 2, up, down, plus alpha 2, 1, down, up, plus alpha 2, 2, down, down. That was our 2-qubit system. And so I'm just waiting for our column right here. What do we put? Well, if you would put these items right here. That's in your column right there. So if this were both ups right here, that means this system is in the up, up. These would all be 0, and that would just be 1, because they have to be normalized. So it would just be this. So up, up would just give you that. And if we multiplied this by, it would give me the same thing, because this first one would be 1, and then you get a bunch of zeros. The next one, they don't match up, so you get 0, 0, 0, 0, and it would just give you up, up. Right here. So up, up just goes to up, up. And same with even up, down. It's just doesn't change. Why? Because if whatever the control, the first bit is, if it's up, it doesn't do anything to the second one. So this would just stay up, down, up, down, up, down. You'll notice up, down, this term would have been 0, 1, 0, 0. You would have plugged in a 0, 1, 0, 0, and you would have got the same thing, 0, 1, 0, 0. But now if I have a down, up, what does that go to? Well, if this is a down, then this guy flips. So if the first one's a down, the second one flips. So this flips to down, down. And we might as well do that, see if it does flip it right here. What did we say down, down was? Down, down is down, up. This is what we're plugging in. So you got alpha 2, 1. The third one is 1. The rest of them are zeros. You'd have like this. And if we multiply this thing through, you get zeros. You get zeros. Even on this one, you get 0. And then you get 1. And that state is just that one, which is down, down, so on. And the last one here, which was down, down, all it would do is flip the last one right here, make that down, up. Okay, so that would be what we call the truth table for that right here. Now, what happens if we put one of these with one of our H's right here? That is, what if we have an H here running it into my NOT gate right here? Okay, and let me put in something. How about if I just put in a down and a down? I'll just randomly pick in a down and a down. Okay, so that's what I have right here. So right at this point, the composite system is just down, down. That's all it is. Where this is the first one and this is the second one. Now the first one goes through an H gate. So we can say, what do we have right there? Well, what does the H do? The H right here, the H, what did we say the H did? Maybe we can just say it right here. What did the H do to my down state? Well, it turned it into a left state right here. So right here, this just turned into a left state right there, and this is still the down. So at this point right here, we're in the left down state. Right there, that's what we are right there. Now I don't want to, just so I have them all ups and downs, let me turn that left into an up and a down. So if I turn this left into ups and downs, remember that was 1 over the square root of 2 up minus 1 over the square root of 2 down. So there was my left, and then we still have our down right there. Or if I multiply that through, this is 1 over the square root of 2 up down minus 1 over the square root of 2 down down. Okay, so that's what I have right here. Now I ask, what do I have right there? Well, I don't touch the first one. The first guy stayed, he never gets touched across here, so it's still going to stay the same. But the second one right here is going to change anytime the first one is a down. Well, you notice the first one is a down right there, so that's going to flip the second one. That's all that's going to happen over here. So at this point right here, what we have is 1 over the square root of 2 up down minus 1 over the square root of 2 down up. Oh, okay, that gives me, that looks kind of familiar. I guess we erased it from the last one, but that was our quantum entangled state. That was one of the 4 in quantum entangled states. How do I get the other 3? Put the other 3 in here. If I put up here, I get a different quantum entangled state, up, down, up, and down, down. Those were the 4 maximally quantum entangled states. So I can use this H gate to make them quantum entanglement right here. Well, what if we put 2 gates, let's say like this, right here. We have a gate here, it could be, say, an X gate, and we have, say, a Z gate. Sorry, don't write it like that. We have, this is now one big 2-input gate right here. What's the matrix whenever you put 2 of them together right here? Well, the rule is at the first gate, let's just say it's a 2 by 2, A, B, C, D. Let's say that was your first gate. And the second gate was a different, maybe it's E, F, G, H. Now, when we combine them, we have to tensor multiply them. How do you tensor multiply? We know how to do 2 vectors, but how do you do 2 matrices right here? Well, if you know it's going to be a 4 by 4, and what you do is you just copy this down, E, F, and E and F, G, H, G, H, E, F, E, F, G, H, G, H. Okay, so all I did was take this and put them here, 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 and here to make a 4 by 4. And then what you do is, for these 4, you multiply them all by A. So A, and A, For this group of 4, you just multiply by B, 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 and B. This one over here, you just multiply them all by C. And this one, you multiply them all by D. That would have been the matrix for the 2-gate, 4-dimensional system. So for us, right here, what did we say? If we wanted to do that for our case, right here, for an X and a Z, the X was 0, 1, 1, 0. So this one was 0, 1, 1, 0. And this one over here was my Z gate, which was right here, 1, 0, 0, minus 1. 1, 0, 0, minus 1. Okay, so what would I do? I would take, and I'd have a 4 by 4, and I would take this one and put it 1, 0, 0, minus 1. 1, 0, 0, minus 1. 1, 0, 0, minus 1. 0, minus 1. Okay, and now I multiply all 4 of these times 0. Well, that's just going to make that 0, and it's going to make that one 0. I take these 4 and I multiply them by 1. Well, that just keeps them the same. I take these 4, multiply them by 1. That keeps them the same. Take these 4, multiply by 0. It just makes those two both 0. Okay, so that's what that would be right there for the matrix. So I could operate on any 4 vector right there. Okay. Now, all these gates right here, you can trying to make code out of these. There's not a lot of codes that you can make with a quantum gate. 2 in particular that are very important, and one of them is called, I guess I can just write over here. One of them is just called Grover's method, right here, or algorithm, by someone by the name of Grover. He wasn't from Sesame Street. Okay, so, but this was discovered in 1996. 1996. And this has to do with searching, right here. Searching, that's all pretty much Google does is search right here, but it's important for computers to find things, finding one thing that's different than all the rest, right here. And so you could be searching for almost anything right here. And normally when you want to search something, let's say you have 1 million places to search, and you want to ask, how far do I have to search before I get a 50-50 shot of finding what I'm looking for? Well, if you're trying to find 1 million things, and you want a 50-50 shot, you're going to have to look at like 500,000 places to get a 50-50 shot. You have to search 500,000. So to get a 50-50 shot, you really have to search n over 2 places. But with a quantum computer, you don't have to search 500,000 to get the same number. You only have to search the square root of the number. So the square root of 1 million is only 1,000 places. So it goes as the square root of n, which is much quicker. Right? And so if you're looking at trillions, the square root of, here you'd have to search for 500 billion. Here, it's just 1 million. Big difference, especially when this number gets really large. So that's one of a routine that makes it a little bit easier to do searching right here. And then another routine that's really good for quantum computers, another method, Shor, someone else came up with a different one, which is 1994. You notice these are all quite recent. He figured out how to factor efficiently, factoring integers right here. You notice computers can multiply integers together. If you have, let's say, 2 big prime numbers. When I say big, I mean a 200-digit prime number and a 200-digit prime number. You multiply them together and you get like a 400-digit product of 2 prime numbers. product of two prime numbers? Well, computers are very fast at multiplying, but what they have a tough time is going in reverse, factoring a 400-digit product of two primes into two 200-digit prime numbers. You know, the fastest computers might take thousands of years, maybe millions of years to do something like this. And so this is one thing that Shor's algorithm will allow you to do, is to solve this exponentially faster. And this is this is how secrets are kept with your bank account right here. You know, this number right here can be known to everyone because no one's going to ever try to factor it. And this is how they keep your banks, your accounts, and everything else secret, is by one person having this number and one, I guess, having the other one right there. So this is one thing. You know, you can see people like the NSA maybe wanting to break everyone's codes right here. Now, you know, the problem with quantum computers is something called decoherence. Remember, we're looking at individual states right here, and they want to mess up, you know, it's just an infinitesimal amount of little disturbance messes them up. We call it decoherence. And so just trying to keep this thing from messing up on the order of microseconds, millions of a seconds, is a hard thing to do. So you have to do you don't get to calculate very long. I imagine as time goes on, they'll last a little bit longer. They need these things to stay stable, you know. And right now, there's just too much noise in most quantum systems. Right here. Okay, I went through these gates right here because the last one I want to do on quantum qubits is quantum teleportation. And that way we'll put some of these gates together and teleport a bit. Okay.